Welcome to Brain Vision.
Well, we have my mass. Let's write down mm for my mass, and that is equal to 70.0 kilogram. And the rock's mass, mr, that's rock's mass, is 15.0 kilogram. And I throw the rock with a velocity of 12.0 meter per second. So velocity of the rock is equal to 12.0 meter per second with an angle theta that is equal to 35.0 degrees. Well, we know that the total momentum of a system is the vector sum of the momenta of the individual particles that make up the system. Therefore, we have total momentum is equal to momentum of particle A plus momentum of particle B plus momentum of particle C, and so forth, right? Well, if the motion is in a plane is two-dimensional, then the equation becomes momentum along x-axis is equal to momentum px, right? So momentum of x, momentum of particle A, or we can say momentum of particle A along x-axis plus momentum of particle B along x-axis, and so on. Similarly, total momentum along y-axis is equal to P by A plus P y B, and so on. Well, let's call this equation number 1. So this is equation number 1, right? Well, momentum is given by, momentum of a particle is given by mass times velocity. Let's call this equation number 2. Well, we also know that for an isolated system, each component of the momentum of the system is separately conserved. Therefore, Px, which is momentum along x-axis, is equal to a constant, right, for an isolated system. And similarly, momentum along y-axis is also constant. Well, this is true for an isolated system. Now let's do calculations. Well, for the horizontal direction, since the surface is frictionless, the momentum is conserved in this direction. So P1 x is equal to P2x, right? But both I and the rock were initially at rest. Therefore, P1x is equal to 0. So we get P2x is equal to 0, and let this be our equation number 3. Well, for the vertical direction, there are two forces, gravity and a normal force, act in this direction. So the momentum is not conserved in this direction. According to Newton's third law, when I exert a force on the rock, it exerts an equal force in the opposite direction. The normal force increases in order to compensate this increment in downward force. Therefore, we have V my 2y is equal to 0. Now, applying equation 1 in equation 3, we get, applying equation 1 in equation 3, we have, let me do it here, my momentum plus rock's momentum is equal to 0. We are talking in the x direction. Now applying equation, let's call this equation number 4. right? Now, applying equation 2 to me and the rock and substituting to equation 4, we have mass of my times velocity of mine, right? Plus mass of rock uh, times velocity of rock, right? And that is equal to 0. Okay, so let's call this equation number 5. So this is equation number 5, right? Let me scroll down. Okay, so my whiteboard is not working. Okay, now it's okay. Now, taking plus x in the direction of the horizontal component of rock's velocity, first we use our values for v and theta to get the horizontal component of the velocity of the rock after throwing it as follows. So we are 2x is equal to v times cosine theta, right? That is equal to 12.0 times cosine of 35.0, that is equal to 9.83 meter per second. And now let's plug in values in equation number 5. Then we have 70.0 Vm to R plus 15.0, right? It's 2x, excuse me, not 2r, since we are talking about x-axis, plus 15.0 multiplied by 9.83. Well, that is equal to 0. So my velocity along x-axis is equal to minus 15.0 times 9.83 divided by 70.0, that is equal to minus 2.10 meter per second. Okay,